Events. A, okej. Dobra. To duże opóźnienie. Okej, to się dostosuje. Okay. The von Neumann architecture is an architecture that has been theorized by Mr. von Neumann. And it has actually been constructed for the first time as part of a CPU in a mainframe in Manchester sometime in the 60s. And the idea is basically the following, is that the processor has two different streams of inputs. One is the data and one of the is the instructions to carry out. And obviously it's creating the output. And this is actually, to an extent, how every single processor works nowadays. You know, it doesn't matter if it's an ARM or an x86 or something like that. Roughly it works like this, not exactly, but the general idea is still there. So you have your instructions, which are your machine code or your assembly that go into the CPU, and they're on like a little stream. And when you have some loops or some control flow or maybe some function calls, there's an instruction to kind of scroll around your instruction list, right? And then you also have the data, the stuff that you operate on, and that gets loaded into registers. So there's a very clear divide between registers and the instruction that's being carried out. It's not really, mix and match between data and instruction. And they create output, which is basically outputted into registers again. And there's obviously a load instruction, which gets you the data into registers, and obviously there's a store instruction, which gets you your data into the output. There is, however, one little change nowadays, is that the data and the instructions can come from the same memory, the random access memory, your DDR. It's not like you have two separate rolls of tape that go into a processor like in the old days. Yes, but there's two different kind of pipes where it goes into the CPU, because the data actually gets fetched through a memory control unit, which talks with your caches, reorders, reads and writes, synchronizes stuff, handles atomics, and well, yes. There's dual channel and quad channel RAM. So the idea behind dual channel and quad channel RAM is that the channels are able to service your requests at the same time. So basically your CPU is actually not in control of the memory operations that it's doing. It's actually the memory control unit. Which can be built into the CPU, into the same die, but it's like a small little microchip and a little processor on its own. So the CPU will maybe manage the page table, which maps your virtual addresses to your physical addresses, while your memory control units would actually be issuing the requests to fetch data from RAM sticks. Because the idea behind quad and dual channel memory is very similar to RAID with disks, is that a certain type of RAID, like RAID 0 or something like that. I think it's RAID 0. I don't know. I'm not really a I/O and network guy. I've got my disks in RAID 5, but that provides redundancy. But generally the idea is that if these are your RAM sticks, then your data is actually laid out, so it kind of like, I shouldn't really be drawing like this. I should be drawing it like like this. Okay, so basically the memory is kind of stippled through your RAM sticks. So for every little bit of data, each of the RAM sticks would have a bit of it. So that, for example, when you want to fetch, a few hundred bytes at once, or maybe, like an entire cache line or something like that, you'd be getting it across all 4 channels at the same time. Just to, make that whole request a little bit. It doesn't make it faster, but it makes the bandwidth bigger. Like, it makes the size of the pipe bigger. It doesn't make the water that flows through it any faster. So the gigahertz is still the same. It's just that the motorway is wider. That's the whole idea. Okay. So essentially, what happens with the CPU and this whole von Neumann architecture is that instructions go into their own separate little buffer and its own little input pipe, and the data goes through the MCU. And this is very nice for the CPUs because they're able to do stuff like predicated execution, branch prediction, prefetching. Because there's 2 separate units in the CPU. There's basically, for example, L2 and L3, at least in x86, they're unified caches, so they're the same. They're a cache that can contain both data and instructions, but at the level of the L1, I haven't heard of a processor that's at x86 that does this, where an L1 would be unified. So L1 is actually L1 cache for data, and then there's a different portion which is for instructions. Yeah. So there's basically a hard divide, and then in one side only data goes in, and on the other side only the instructions go in. And obviously there's like a logical sequence of instructions that are gonna get sent to the CPU. So this is more to do with like how the binaries get executed and how the operating system kind of pushes the instructions along to execute. So that's basically it on like the von Neumann front. If you want to go into it deeper, and there's lots of good resources about that. And the reason why we talk about this is to understand how function calls get implemented. Because with function calls, what you have is basically you have an instruction that tells you to jump to a different address in the instruction stream. So basically, when you have a function call, the function call, what it will do is, if I go call some function, and then what that will basically be is pushing current stack frame so you stack frame. So you basically know the address in the instruction stream to jump back to after you're done with the function call. So that gets pushed onto the stack, and then also the variables, the arguments for the function that you're calling. So if you're calling a function which takes an A and a B, then those arguments will get pushed onto the stack. So you're pushing an A, and a B, and the idea is that this function will do its whole instruction stream, and at the end of the the instruction stream does basically a jump back. So when you enter into the function, the function looks at what is the current value of the stack pointer, and then it allocates all of its local variables, like the stuff that you might want to declare that's not allocated from the heap. So, if you have like some int, if you have some small array, or if you have a small struct, that goes onto the stack by just incrementing the stack pointer. And then at the end, when those variables go out of scope, the stack pointer rewinds until it rewinds to the arguments of the function itself. And obviously what arguments the function takes, from its signature. So you can rewind back to them, and then you're back at the place where the address to jump back to, the continuation address, is pushed. So you just do, at the very end, you just do, you do a pop A, you pop all the arguments, and then you would just basically you do a jump to a whatever address you've popped, right? So this would be either runtime jumps or relative jumps, because because of the way that recursion works in C, C++, and pretty much every other language that's kind of quite low level, is that your stack addresses are floating. If it's the first call to F, then the local variables are going to be in a different place on the stack than if it's like the 50th call to F. So you never know, you don't know where exactly in absolute terms on the stack your variables will be allocated, but you know where they will be allocated relative to the stack frame at the beginning of the stack pointer at the beginning of the function. So everything is done relative. And also the jump back to the address also has to be a dynamic address, can't be a constant address, because you don't know who called the function. So as you can see, you've got the instruction streams. They can be embedded in the random access memory, or they can be in a file, which is your binary, that need to be read. And the call is basically a jump to an address in the instruction stream. And obviously the instruction stream knows when it's ending, because if it's in order, we're walking through it instruction to instruction. At the end of it, there's either going to be like a jump or a program termination or something like that. So that's how you're able to have data and instructions all over your memory in a binary. And this leads us to how is virtualism implemented. The basic thing about virtualism is that if you have a hierarchy, so if you have like an object, actually I'm not gonna call it object, I'm just gonna call it a type called thing, and then you have your you have your animal, you have your inert, and then you have your chair, and all sorts of things like that. Animal, have a cat and dog. So if you actually have a base class for this, then if it has some virtual methods, then when you want to use a dog as a pointer to a dog as a thing, then each kind of instance of thing needs to have a pointer to a virtual function table. And what this virtual function table is that it contains all of the addresses of the functions all of the addresses of the instructions that define a particular implementation of this virtual function. And if we just go over to like an actual example, so you can see here that we have some classes which I've shamelessly ripped from C++ tutorial. Is that this person is our base class, and this baseball player. Oh, sorry, you haven't switched yet. There's a delay. All right, so there's basically a different example. Can you see it yet? Okay. Okay. So we have this thing called the person, which is basically this top level thing, and then you've got this baseball player, and you've got this employee, and this is very, very, very like basic inheritance, because there's no virtual functions. There's just some overrides, and basically it's not really doing much, because it's this yeah, of course. So one of the cool things that you really want to be able to do is, for example, if we make this function which is like print name, right, and it will take a person. It can be a pointer, or it can be a reference, doesn't matter. It's just a matter of notation. We can make a reference, we can make a pointer. As long as it's a pointer or a reference, then this concept applies, because if you're gonna pass by value, then this will actually need to be a type of person, as in this will need to be a variable of type person that goes in. And if person is an abstract data type, basically what we call a what's it called? Basically, so I'm just gonna add one more function. Okay, get nickname, right? And this was what we call a pure virtual function. So a pure virtual function is a function that's not it's not intended to be implemented by the base class. So this base class expresses some abstract ideas which we cannot define for the abstract thing. So an example would be, for example, a class called animal, or an animal class, and you'd give it a function called eat, right? So before you know what kind of animal it is, you can't really define how it's going to eat. So this is like a perfect case of something that would need a pure virtual function. So because it expresses an abstract idea that an animal eats, but there is no such thing as like an object animal. It's an abstraction. There are particular animals. Yeah. So so an abstract data type is basically something that has some pure virtual functions, pure virtual stuff inside. And what we'd really, for example, like to achieve is, for example, to have some function that can process any type of person or animal. So we want a function that works with an abstract data type. So I'm making this function called print nickname. So this person will get their nickname. And the idea is that if this baseball player, and in this case you don't need to put down virtual, because you only need to put down virtual if you expect that there's going to be a class which is going to be overriding this function. So, for example, you've got get nickname, and I'm gonna return hotbob. Obviously, with C++11, we've got a new keyword called override, which I suggest you use liberally, because it will catch all sorts of problems when you've been meaning to override a virtual function, but for some reason, for example, the type doesn't match, and it doesn't override. So we can do print nickname on Joe, and we can also do print nickname on Frank. All right. So there's two things I want to show you. One of them is obviously this is the polymorphism, which const. Okay, that's because I put const. Okay. Always use const references, but then if you use const references, you can only use const functions. So, and these functions, not const. Okay, so we've got nickname hotbob and then nickname boring Gerald. And the whole idea is behind this is that when I'm passing this reference, because at this point it's a reference, we can also make it a pointer. The underlying implementation by the compiler is almost the same. So when I'm passing this pointer doesn't actually, or this reference, it doesn't actually know, well, it does know, but we'll get to it. But when you're passing it, it's not, how would I say it? The function doesn't know anything about the argument it got called with. The function itself has no way it has no way to know what's the type of the object of this person. What's the type of this person? And the way it actually gets done is when the compiler actually implements your class, and this used to happen a long time ago as well, like quite literally as I'm saying it. C++ used to be compiled to C. So the compiler, 10 years ago would have taken all of your C++ code and turned it into C code, and then that would go through a C compiler. Now it kind of goes directly, but the idea is that when your compiler would turn C into C++, more or less the following would happen. So there would be a struct called employee, and as long as you didn't have any virtual functions, it would look like this. So I'm just going to comment out virtuals. So what it would look like is basically you'd have this struct employee, and then all of your members of the base classes would get copied in. And they would get copied in exactly in the order that you inherit. So if you're inheriting from person and then person inherits from something else, the top level parent would get its members declared first in your I'm just gonna call it employee C. So this is what your compiler would have done 15 or 10 years behind the scenes. So first all of your members would go in, and then all of your all of your parents exactly in the order of inheritance, and then at the end of it there would come your own your own members. Well, only if I declare a virtual destructor, because right now I don't have a virtual destructor in here. Yeah, so we'll get to how this get worked out. And if you actually do this, if we actually do it like this, so I'm just gonna do a return 0, and I'm gonna print out to you cout. I'm gonna show you what is the size of this employee person. Employee std endl. Okay, and then okay, and then I'm also gonna print the size of employee C. Okay, so I'm gonna run this, and sorry, this function now doesn't compile because there's no definition. Okay, so I'm running this. Oh, for God's sake. Okay. Yeah, I just forgot about a few things. Okay, so if you see here that my C++ struct is 32 bytes, and my C struct, which is your compiler behind the scenes, is also 32 bytes. And if I were actually to do offset off, which, you know, do you want me to do it for you? Or do you consider that a waste of time? Okay, so there's a nice little macro called offset off, and it's nice because it can show you it can report to you the byte offset of a member. So I'm gonna do employee. It's a compiler macro. It tells you what's the offset of a member in a struct by a byte offset in bytes. Expected a primary expression before the okay. All right, so I need to add an include for offset off. 1 second. What's the include for the offset off macro? Okay, that's std def, right? Okay. Okay, so yeah, so I'm just gonna quickly do my little thing. Okay, so we've got my name, my age, or member, hourly salary, and employee ID. Okay, so I'm also going to do the same for my C class. Okay. So as you can see, my offsets match perfectly. The C class and the C++ class, the C struct, which is what I call the behind the scenes compiler struct, and as well the layout of all of the members of employee is exactly the same. But this is now because I can use employee in a function, no problem, as a person. It's absolutely absolutely no problem. But the problem is that now when I pass this employee or this baseball player to a function which is working with the person type, is that if I remove this virtual keyword, I'm just gonna remove this really quickly, then I've got no polymorphic function. It's not a virtual function. It can be overridden, but the override does not kick in if I don't know the type. So if I pass this baseball player or this employee into the print nickname function, and I've got this get nickname function, which is now not virtual, right? Then now my print nickname function will not know that there's an override. So if you look at it, here is, oh, what are you doing? Okay, that seems to be a pointer. So basically what will happen is that it will not know that the person is of type employee, and what you'll actually get printed out is an error. Yeah, nickname error, nickname error. But as soon as I change it to the correct type, which is the employee, and obviously I need to not print out the baseball player, then you get nickname boring Gerald, because the function now knows the type. So this is an example of, okay, so because I've changed the type in the function to employee, it's printing, yeah. Yeah. So this is a function that you can override. You can override it, but it's not polymorphic, kind of. Yeah. Correct. That's kind of more or less how it goes. Okay, so the very first thing you need to understand is that when you have a what's it called? Sorry. So the very first thing you need to understand is that when you have a class, the function definitions are not inside the class. This is the thing that we talked about with the instruction stream. So when you have the instruction stream, the instructions are compiled in a completely different place than the data. So the okay, that's strange. Hello? Hello? Okay, interesting. Okay, so I guess I just sit and wait. Little technical break. Yeah, so just to answer questions from the viewers, it seems that we lost the Skype connection with the master of this masterclass, so just gonna sit around and wait for him to reconnect. But if anyone's on the masterclass channel, then you can ask any questions, I guess, and I can answer them in the spare time while I wait for the master to reconnect. I'll try to call the master again. Okay. Hello. Yeah, you just disconnect. Oh, you lost your connection. Okay. Cool. Oh, okay. That's a bit strange. Okay. That's a bit... Okay, so under the hood. Under the hood basically works very simply, and I was about to show you, and I've actually gotten it down, is that as soon as I add a virtual function, the every single derived class starts needing a virtual table. So as soon one of the parents has a virtual function, for example, a virtual destructor, all of the children will start needing a virtual function table, and because they start needing a virtual function table, is their size grows by the size of one pointer. So you can see that the size of employee is now reporting 40 instead of 32. So it's 8 bytes more, and then at the very start of this, every single struct, at the very start, not in any other place, at the very start, you have your virtual function table pointer. So as I told you, because you've got the separation of data and instruction streams, the virtual function table does not sit inside every single class, and as well, that would be just a waste of memory, complete waste of memory. So you don't have a pointer to every single virtual function implementation at the start of your object. You just have the pointer to the table, which contains a pointer to every single function implementation. If you get what I mean. So yeah, if we look at this offset off the name, right? Now I need to add this again. Now include cstd-def. It's compiling. So if you look at offset off, wow, it's taking a long time. Come on, please work. I'm just gonna have to maybe wait a little bit for it to compile. But yeah, the basic idea is that if you look at the offset of the very first member that you're gonna encounter, is that essentially when you're looking at the offset is gonna be off by 8 bytes. And 8 bytes is the size of the pointer on this particular architecture. If you were compiling in 32 bits, then maybe this pointer would have been, oh fuck, great, thank you so much. It's just deciding to die. The C++ compiler. Maybe I'll find a different one. Yeah. Because I don't want Godbolt. I want something. Oh, online GDB. Okay, that's the one. Yeah. So CPP shell is not exactly the greatest thing on the planet. It likes to just die for no reason. Okay, so stdcal, and I'm gonna just do the offset off employee. My name and std end line and we're going to include std-def. std-def. Run. Oh, seriously? Okay, so it's here. I think I just got. Did I get this the wrong way around? You gotta be. Offset off. Offset off. I was just a little bit too eager to get this type. Okay. Okay, so you can see that now the offset is 0, and as soon as we put in this virtual function, which is the destructor, we'll get a offset of 8. Run. Hey, ta-da! So this pointer goes to a table, the virtual table pointer. So this is very nice because what it's able to tell us, two very nice things, is that this pointer, when it points to the table, which is data, but it also points to instructions, it's able to this virtual table pointer is always at the start of the object. So when I'm passing a pointer to another function, right, like such as that print nickname, right, I know that at the very first 0th byte there is the pointer to the virtual table. So as soon as I get this person pointer, right? No, just got John Doe. So as soon as I get this this pointer, I know that from this very start of this object, I can infer its type. Because at the very start of John Doe, which I've just written, there is a pointer to the virtual table of virtual functions. And then this will essentially tell me this table, which is it's only one big piece of data that is shared between all of the employee types. There's one virtual table for every single type. So this one virtual table, first of all, it tells me that this is an object of class of type employee. Like the most derived, like this, the actual type of this is not person, it's not baseball player, it's employee. Yeah. Okay, so in the constructor, when the constructor gets called, the 8 bytes at the front of your object, that's the pointer to the virtual table. But the virtual table itself, you can say that it doesn't take up any memory. Well, it does take up some memory, but it doesn't take up memory per object. Do you understand what I mean? Yeah, exactly. It's basically like a static thing. Most of those things will get compiled in at the start of your library or at the start of your binary. Like at the very start, there's basically like this global and constant static data section. And that's kind of where all of this kind of assembly code or machine code will live. Probably, but it's implementation. It's implementation defined. So between different, there's no standardized way of laying out this virtual function table. On GDB, it's gonna on GCC, it's gonna be different. On Visual Studio, it's gonna be different. On Clang, it's gonna be different. And even more importantly, it can change between compiler versions. So because C++ is not application binary interface compatible, if you want to make a dynamic loaded library like a DLL or something like that, all of your front-end API needs to be in C if you want to be able to link it at runtime and mix a library that's been compiled with a different version of the same compiler even, let alone a different compiler. So if you wanna make a library which will play with whatever compiler you're going to use to compile the code that uses the library. So for example, if you're making like a driver for a graphic card, or SDK like optics or something that's really closed source, that you still need to distribute the libraries to, like fmod, then what you need to do is have all of the front-end API in C, not C++. Because C is ABI compatible. There's a standardized way to basically lay out all of the pointers. Because in C, the only thing that you have is just function pointers. Function pointers have a signature, and once they have that signature, it's like there's not a lot of free leeway in laying out and kind of the layout of a function pointer and a function signature. I mean, well, the function signature is just basically the type that the type that it returns, and the types of its inputs and how many there are. So, if I was gonna and the types of the parameters that it takes. So for example, if I was to declare a function pointer to I might be able to do it like this. I'm just gonna check if I got the syntax correct. So that would be, oh sorry. It seems to me that I forgot how to declare function pointers, because I usually just, nowadays I just do auto. Nah, I got it. I think I definitely got it wrong. I think the compiler will tell me what's the signature. But that's lagging. Okay. Yeah. I'm just looking for. Oh, okay, that's the one. Sorry, that's how you do it. The signature. So the syntax for a function pointer is a bit weird. Yeah. So that's how it looks. What? Don't be stupid. Okay. Yeah. So I've been using too much auto recently until I reached the point where I forgot the syntax for the bloody function pointer. Yeah. Yeah. Oh, punk. Okay, yeah. Yeah. FP. Yeah, FPTR. Sorry. Yeah. It doesn't deduce at runtime when you use auto. It deduces at compile time. Okay, so this is the stupid syntax for declaring a function pointer. Like the name of the variable goes here, which is a bit weird. So what you can do instead is do an alias. Yeah, but if you're writing libraries and stuff like that where you actually do need to know the type, or using libraries, then you're gonna see a lot of this. So you can actually declare this like that. And then this will work. That's that's kind of that's kind of the syntax that I'm used to, is that first we declare an alias or type def for the function pointer signature type. This is how you do it. And then we kind of use it as like a normal type. So we use the alias or the type def to go with this. It makes for much cleaner code, because anyone that writes code like to declare a variable like this, if you do that, then you deserve to be fired. This is what type defs are for. So when you're loading OpenGL functions or Vulkan functions and stuff like that, then you need to pay attention to this, and also doing runtime linked libraries. And yeah, so basically okay. Oh Jesus. And I mean, the screen doesn't even move. That's just a shame. How is it looking now? Okay, yeah. So basically, if you add one more like variable, then you need to obviously update the function signature accordingly, because basically, so this is what I say about C being ABI compatible, whereas C++ not, because in C there's no inheritance. Well, it kind of is, but isn't. So when you actually, as in, in C++ you can declare a struct which inherits from another struct, but there is never any virtualism. There's no virtual pointers. In C, there's no virtual, so there's no virtual functions. There's no runtime polymorphism. There are if there are no overrides, I think, as well, if I remember correctly. It's a long time since I last programmed in C. So basically, from the type, you know exactly the functions that are gonna get called. So like a method in a struct in C is more like a function and a function with an implicit first argument, which is basically this. So there's no leeway between compilers, because when you have a class in C++, first there's the question of the virtual table pointer. Then there's the question of templates. There's a thing called name mangling. If you actually open the GD, if you actually open the glibc, then you can see like the name mangling. So for example, something like a string is actually a template of the character type. As in, if you don't use type defs for function pointer type definitions, then you are making the code really illegible. Like it's not gonna be easy to read at all. Yeah. So going towards templates and stuff like that, if you have a templated function, if you have like a templated class, so if you actually open the standard C library that gets shipped with GCC and look at the symbols that it exposes, is it practices something called name mangling. So it basically inside the library, if you actually look at the symbols, it's going to look as if the compiler has compiled that C++ into C. Kind of. It's not doing that anymore, but it looks like it absolutely has. So then it will do some mangling like char, and then just adds lots and lots of stuff like at the end with underscores. So that's basically mangling. So every single type or function that you declare as a template, it will basically export a type name with like some kind of a unique ID at the end. So you can kind of find it in the library or in the executable. So whenever you instantiate a template of, for example, a template function or a template class, you can pretty much think as this whole class is getting copied and stuff is getting changed in it, and it's also getting a different name. Yeah, and function as well. So this is why template. Yeah, there's yeah. Yes, of course. Yeah, of course, it has to be cached. Yeah, it wouldn't work otherwise. So it's cached. So a compiler has a cache of the different types that you've instantiated templates with, and it will find if you have done it before, it will find it, and if not, it will construct this whole class anew. I had this a trick to change a string into a unique type a long time ago. So you can use this thing called variadic templates, where you can have like, you know, just a variable amount of inputs. So I wanted to use templates as a I wanted to use templates to speed up looking up static strings translated to different languages. So what I wanted to do is basically use a string as a template type, but you can't use a string as a template type, as a template argument. The only thing you can use as a template argument is a type or one of the plain old data constants, constant expressions. So constant expressions of integers, constant expressions of, you know, just basically integers, not, you know, not strings, not floats. So I came up with this idea, I borrowed it from somebody else actually, is that basically I make a variadic template. And I will disassemble a string into its separate characters, and then I will put that into a variadic template where every single character in the string is a template argument. So I borrowed some code which was kind of quite recursive. So it would build this unique type out of multiple unique types that it inherited from. Where, you know, the type would be just basically the string but one shorter. So, and it was trying to do this really clever kind of thing, you know, when it would just basically, you know, take one off the end and you know, just keep going, you know. And the problem with that is that essentially what happened is that so many different types got instantiated because I was using about 2,500 strings, you know, with different kind of phrases in the program. So I had 2,500 strings, and each one of those strings was basically making a whole bunch of like parent types, and there were as many of them as the string length. So if one of my strings was maybe 180 characters long, then it would make one with that string, and then one with 179 characters of that string, and one with 178, and so on until it got down to one. And the problem was that because I had 2,500 strings, each of them was making on average about 100 new types. Then the compiler had to make around about 200, so between 250 to 200,000 unique types in that cache. And that's how I managed to crash the Visual Studio compiler, make it run out of memory. When compiling one file, because this one file was instantiating a template with, you know, hundreds of thousands of different template arguments, you basically ended up with the compiler having to cache that 2,500 different kind of combinations and also generate code for that. So that's when the memory usage of the Visual Studio compiler went past 16 gigs. And the compile time was something like, you know, 3 hours or something like that. So this is why certain programmers don't like template code. Like why some might find GLM code a little disgusting or not very usable, because, well, what they claim is that there's so much template stuff going on in there that it significantly increases the compile time, because, you know, all of those different unique types that needs to get generated at runtime. But because it's generated anew with the whole new types and just the whole function gets copied, it allows for really high runtime efficiency. Because when you have templates, that allows for static polymorphism, and, you know, like for example, static if statements, which basically get optimized at compile time and stuff like that. So templating can trade some compile time for quite a bit of runtime. Because static polymorphism is a lot cheaper at runtime than dynamic polymorphism, runtime polymorphism. Did you get what I mean? Okay. So why is the virtual destructor so important? Because see, the delete function, nothing's gonna happen if you just make a function, if you just make an object on the stack, then nothing's really gonna happen. Because when you make an object on the stack, like for example, baseball player Joe or employee Frank, the function that you're in, the one that has the stack, knows what exact type of Joe and Frank are, so it can call the correct destructors. So if we actually do the employee destructor, sddcal, employee died, because coronavirus, and then we have our baseball player. This one's gonna be season cancelled. And then if we actually do our, here it is. A person has already a virtual destructor. Cannot be a virtual destructor. Cannot allow for that. Okay, and then the destructor of person will say coronavirus. So because my little objects are on a stack, the compiler knows exactly what type it is, and it knows to first call the derived class destructor, because it calls everything in destructors and constructors get called in reverse order. So if I declare two variables on a stack, they will get destroyed in reverse order. So if I've got the baseball player and then I've got Frank, then first the employee will get destroyed because he was created last, and the baseball player will get destroyed last because it was created first. So it just works just like the stack, first in, last out. Because it's the temporary storage is a stack, it unwinds in that order. So, and also with constructors of base classes and derived class, when you go into a constructor of a derived class, such as an employee, first the base class constructor will be called, even if you haven't actually called it manually. It will just get implicitly called. And then the rest of the constructor for the derived class runs. And with the destructor is exactly the opposite. First, the derived stuff gets called the destructor upon, and then the base gets called the destructor. So you can see that the employee died, and then the person died. Well, as in the employee got called the destructor, then the person destructor. And then for the base player, first the base player destructor, and then the person destructor. And this all works because you're on a stack and you know the types of the stuff. But if you start using heap memory, my friend, then we start having a problem. Dynamically allocated memory. So this is where not using a virtual destructor is going to trip you up. Any class or that you're gonna be using with dynamically allocated memory, basically not just solely on the stack as temporary variables, any class like that needs to have a virtual destructor, unless you have a really good excuse. Because otherwise your base class destructor might have a problem getting called Frank. So if you have a look at this, oh shit, I need a pointer. God damn it. Yeah, I just need to change everything to freaking dereference operators. Okay, change everything to dereference. And then you can see, oh, I really hate live coding. Live coding is not fun. Okay, so you can see what happened here. We still know the type because we've got this pointer type right here. We know that this is a baseball player. We know that this is an employee. But if we change this type just before, so now we're calling delete on a different type of type person. Lots of your management code would, for example, you would want to have like a person manager or like a NPC creator in a game, something like that. Like an NPC manager. So it would always be working with the type NPC, not with the like type NPC enemy and NPC friend or something like that. Then it would be like doing all sorts of like cleanup functions at the end when it would be deleting them. And this is where you'd run into problems. So if I change the type of, which I'm allowed to do, of Joe, this baseball player, to person and employee to person, then I get a problem is that it will only call the destructor of person. It will not call the derived destructor. Only the base destructor will get called. And then anything above the base. So basically for the pointer type that you're at, that will get called, and then anything above that, but then nothing below. And this is a big problem, huge problem. Same thing happens like here, especially if you're making lots of abstract data classes where, for example, let's say you're making a renderer, or and then the renderer would be an abstract data class, and it would have all of those functions like draw, prepare, stuff like that. And then you'd have two different backends. You'd have one for OpenGL and one for Vulkan. So all of your code would be set up to work with this type called renderer, when only this new function here would be new Vulkan renderer or new OpenGL renderer, and then we'd just all forget about the fact whether it's a Vulkan or OpenGL renderer, because this is what polymorphism is for. So you can see that if you just do it this standard way, then you start having a huge problem. And what this virtual destructor allows us to do is basically to allow us to treat the destructor function like any other function. So it's virtual, and it also gets its own little entry in the virtual table. And now, despite the fact, now that I've changed the destructor of person into a virtual function, is that now that I'm working with a person type all the time, is that now when I'm doing delete on this person type, it's actually reaching the derived destructor. So basically, rule of thumb is that whenever you expect somebody to inherit from a particular class, you should make that particular class's destructor virtual. And you can make any function virtual except for the constructor. And the reason for why we don't have virtual constructors is very simple. Because when you are creating an object, you will know what the type is. There's no way there's no way at all in the world to create an object without knowing its type. So that's why constructors are not virtual. Anything else? Yes. And the reason why this is an issue is because with the delete, at least with the delete, is that the delete is an operator. It's an operator of the class. So the class has an actual void operator delete. And there's, when you go on the C++ spec, there's about 14 declarations of new and delete, because it depends on whether they take an alignment hint at the end, whether it's a throwing delete, whether it's a throwing new or non-throwing new, whether it's a new for an array or a new for or delete for an array. But all of those are operators of the class. And new is a static operator of the class, which you can override. You can override new and delete operators. You can make new and delete allocate memory, which is different from the global memory. So yeah. Like we do it in our engine because we need every single object to be aligned to the simmed alignment. So we actually override the new and delete to make sure that when it's grabbing the memory, instead of malloc or something like that, it's actually allocated on memory that's 32 bytes aligned or 64 bytes aligned if that's need be. So we actually have a base class in the engine that every other class inherits from, just to make sure that the alignment is respected, and it overrides the new and the delete. So your final question, which was about the diamond problem and the virtual the virtual inheritance. So with regards to the diamond problem, there's actually two ways to solve it. I'm gonna make a class called professional baseball player, and it's gonna be both a baseball player and a employee. I'm gonna make a professional baseball player. I'm gonna call him Pro. And his hourly, sorry, no, it's kind of, our hourly salary is gonna be a lot of money, and his ID is gonna be 11. I need to give him a constructor as well. Public. I'm just gonna copy that actually, just to not waste time. Employee. Okay, hourly salary and employee ID. See what it spits out. There's definitely some errors in it. For sure. Oh no, actually works. Okay. So I'm just gonna remove some code which is gonna get in the way of understanding the output. Okay. So when you're doing virtual inheritance, the problem here is that when your compiler starts, well, would have started a long time ago, as I said, the compilers are not doing that anymore, but it's possible to write a compiler that compiles C++ to C first. Is remember that thing I showed you about how this whole thing gets assembled for a C compiler? Is that first you have the base, and then you have the what's it called, you have all of the member stuff in the order that it got declared in the inheritance chain. So okay, so if I was to look at this intermediate compiler stuff that gets generated, it would look a little bit like this. So baseball player would start off with a virtual table pointer, then I'd have the stuff which belongs to a person, and then I'd have the stuff that belongs to the baseball player. Yeah. And then if I look at employee, it would be pretty much the same story, except that employee would have different stuff for its own member. Sorry, for its own member variables. So, and obviously this virtual table pointer is not a member. It's not a member variable. It doesn't get inherited or owned. It's just, every single one has a different one. So essentially, when we're making the next one, which inherits from both of them, this is where the problem starts. Is which one of its parents do I get the members for the common base? Right? Because I see if I put them on, right? If I put them on like this, one after another, where I just basically copied. First I copied the stuff from one parent, and then I copied the stuff from another parent. That wouldn't work, this standard method, because I'd have duplicate members. So what this virtual inheritance allows me to do is basically virtualize some of the members. So these members, the members of, if I'm going through this chain, the members of the base of employee, that person, the alias. So you've got kind of baseball player person, right? And then you've also got your employee person, right? And then the employee person and the baseball player person, they need to alias to the same bit of memory. So when you're going through the employee into the person by doing pointer casts, when you're doing those pointer casts, it needs to know like the offset to jump to get the person data. So it needs to know that, for example, the offset of the name or the age that it gets through casting to employee is the same as the offset to the data of person when you're casting through the baseball player. If you follow what I'm saying. Are you with me? Yeah. And as I said, there's two ways. There's two ways of fixing the diamond problem. One of them you can see right now is that it has a little bit of a problem. Is that it's calling a destructor twice. Because in order for you to have absolutely no duplication, you need to have the stuff that's duplicated virtualized. That needs to be virtual inheritance. So actually, right now inside this thing which is virtually inheriting from baseball player and employee at the same time, but it's the virtual inheritance is only at the link of professional baseball player to baseball player and professional baseball player to employee. That's causing a duplicated person. And if I actually remove the, oh fuck, okay, that's strange. I'm surprised that the compiler has even compiled this. This is nasty. So right now I do actually have duplicated persons. It doesn't matter if I put virtual there or not. So yeah, it's strange that the compiler allows this. But if I put the virtual inheritance at the level of inheritance with the thing that's going to be duplicated in the future, so this is for example why all of my classes in my engine, whenever they inherited from reference counted, which is an abstract data type for something that's going to be used with our own implementation of a smart pointer. So this reference counted class, every single time we use that in the engine, we virtually inherit from a reference counted, because it's very likely that I'm going to be inheriting from 3 different base classes or 2 different base classes, and each of them is going to be inheriting from reference counted. So that's why, you need to be vigilant at this stage, the stage of where there is no duplication yet. You cannot fix it at the stage where duplication is coming. You need to fix it, much lower. And now if you have this virtual inheritance here, is that you can see that there's no more duplicated person. So first I get the employee died, because that's the most derived kind of, that's the last thing that I'm inheriting from. Then I get the season cancelled, because baseball player distractor gets called. And then through the use of virtual inheritance, it makes sure that there is no duplicated persons inside, and it's only calling one destructor because there's only one person inside. And if you see the difference in the size of a professional baseball player, so the size of professional baseball player C, which is what's a base a benchmark is against, which is how I think the compiler lays out in memory, is the size of that is 56, right? And then when you're using this virtual inheritance, the size of a professional baseball player is 72. It's most probably sticking in extra stuff, extra pointers, so that you can retrieve the person variables. It's most probably sticking in extra 2 pointers to the person. So that would be, so that'd be 56 plus 8 plus 8 would be 72. So you've got 2 pointers to inside of itself, so it can do the correct arithmetic. But if you do public virtual here, or you don't do virtual inheritance, then it's 88. So you've actually got it's the size of a baseball player plus the size of an employee, essentially, because there's a duplicated person inside. So this is kind of my bad. I kind of forgot about this. Is that here you're gonna have a when you're doing this with virtual inheritance, the baseball player is gonna have a pointer to base person, kind of like that. So instead of the classes that are using virtual inheritance, they're not gonna have the data right below. You won't be able to just go back the size of a person to get your data. You'll actually have to have a pointer to get back to the person data. And this all ties into static cast, dynamic cast, and reinterpret cast. So I'm actually going to talk about dynamic cast last. So okay, I see. But one thing you need to take away from this is, because you have these pointers to the base person, to basically when you have whenever you have virtual inheritance, you will have those pointers. Is that you no longer get the ability to static cast from the derived class into the base class. You need to get dynamic cast. Sorry, the wrong way around. You lose the ability to static cast from the derived class into the scratch. From the base class into the derived class. Because before, if you were an employee and you are at pointer of type person, so if you are with your pointer, if you are here in employee and you are in at the point where you're person, then you can say with static cast that you know that this pointer of type person is actually a pointer of type employee. And because you know the layout of employee at compile time, you know that you can just advance the pointer forward. That's what static cast will do when you're casting from base to derived. You're just basically adding a certain offset to this pointer. And the main thing is that when you're in a class which has virtual inheritance, in this professional baseball player, if you have a pointer of type person, you can no longer do a static cast from this person to a baseball player or an employee. You can no longer do you can no longer do this cast from the person to a baseball player or from the person to an employee, because you've got virtual inheritance. You don't know whether you need to walk forward to here to the baseball player or whether you need to walk forward to the employee. So the offset that you're going to be adding is not going to be constant. So this is why static cast cannot be used when you're trying to go up the inheritance hierarchy from base to derived when you've got a diamond problem. The only way you'll ever be able to do that is with a dynamic cast. And the only way that dynamic cast is able to do that is through runtime type information, which is a special compile flag, which actually embeds even a little bit more data into your structs, not structs, but into your data layouts of your types. And I think that wraps it up. Okay, all right.